All right, good. And we're going to open up my packet tracer program. Did I ever give you a copy of this program?
A packet tracer?
Yeah.
I don't think so.
It's a nice program to have. It teaches you, it helps you to learn about, routers and switches and so on. And we've used it often, you and I, but I don't know if I've ever given you a copy of it.
I don't
Okay,
think so.
let's see. We're going to get a couple of routers. I've got router 0, and then we have, before we do that, let's see what's in these routers. Looks like I've got 2 links. That should be fine. Okay. Okay, I need to build some of these with and have at least 3 in there. One second. Sorry, Sam. I'll find what I need. Come on here. Let's okay, this will do it. Gosh. Let's get rid of these. Put a couple of these in. That there, there, there. One down here. Okay.
Wait.
So, and then let's make a couple of connections. All right, so we've got this network, and let's just move it over here. And we'll squish it up a little bit. Okay, now the next piece I want to do is I want to get that up there like that. And okay, so we've got both screens up here, and you should be able to see both of those, right?
Yeah.
Okay, so let's take everything from the perspective of router 0 here, all the way on the far left, okay?
Okay.
Now, let's say that all of these routers belong to the same AS, autonomous system, and my first question is, who are the neighbors for router 0?
It is router 1, router 2, and router... I can't see 2811.
The router 2811, is that what you're talking about?
Yep.
Is that a neighbor?
No, that's not a neighbor.
Okay, so router 0 only has 2 neighbors, right?
Yeah.
It has router 1 and router 2 as neighbors. All right?
Right.
Okay, now, let's say we're talking about RIP. And RIP is basically going to send its cost, okay, for everyone that it knows about, okay? And the thing that you've got to recognize is that this connection right here, okay? What can we say about that connection?
This one from
2.3 to 2.1.
2.3 to 2.1. They are neighbors, but...
Okay, yes, yeah, that's very good. They are neighbors, yeah. What else can you say?
That they are an OSPF, intra-AS routing protocol.
Okay. Anything else?
And they are OSPF. They could also run on both RIP and OSPF.
Okay. They're all in the same AS, so we could use either RIP or OSPF. Okay. But the point that I'm trying to make is that how many devices are on this network?
Wait, on this?
Yep. How many devices?
Which network? From the router 2.3?
Right here. Do you see where my mouse is? Can you see where my mouse is going back and forth?
It's connected between one other router. There's like 2 devices, router 2.3 and router 2.1.
Okay. on this connection, there are only two devices, router 2.3 and 2.1.
Yeah.
Each router has an interface connected, right?
Right.
And what can you tell me is, what do those two interfaces have in common? What do those two interfaces have in common?
That they are in intra. They are a inter.
Forget about inter. Okay. What do they have in common? Aside from connected to one another, these two interfaces have something in common.
They are your direct neighbors.
Okay, let me try something on you, okay? So let's say I do this. Okay, so I've got two IP addresses. One IP address is for this interface on router 2.1, and this IP address goes to this interface on router 2.3.
Yeah.
Any problems?
They are different IP addresses, so they're not the same IP addresses.
I don't think that's what you really mean. Yes, don't they have to be different IP addresses? Don't they need to be unique IP addresses?
They could be unique IP addresses.
Yes, but what?
But the problem is, it's not on the same interface.
No, not on the same interface. That's not the term you want to use.
They're not. The routers are different.
Yeah, the routers are only different in name, okay? But Sam, this connection between these two routers, okay? Okay, the IP addresses, you're correct. Those IP addresses are not right. I want you to change one of them. For instance, the one in red, the 172.16. What would you prefer I change that to?
192.168.10.2.
Okay. So you're suggesting 192.168.10.2. Is that right?
They can be the same IP addresses, but they have to be unique.
How can you say that? Okay. You say they can be the same, but they have to be unique. You can't do that. You're not allowed to do that. It's got to be one or the other, Sam.
Yeah.
So, do they have to be unique or do they have to be the same?
They have to be the same.
No, they should not be the same. Okay? They need to be different. They need to be unique. Okay? You can't have two interfaces here that have the same IP address.
No, they have to be different. Like
that would be like giving a friend of yours a cell phone with the same telephone number as yours.
You can't have that.
Right, can't have that. So one of these has to be different. So let's go back to this one right here. Tell me how you want me to change it.
Change it to 172.
Okay, no, we're not going to go there.
change it from 10.2 to 10.0.
Nope.
10 dot. 1.
192.168.10.1. Okay. Now, I want you to figure out and tell me, based on the default Class C subnet mask, I want you to determine for each of these addresses, what is the network ID?
It is 192.168.10.0.
Okay. Is the network ID the same for both of those interfaces?
192.168.10.0. Yes.
So we can say that the devices on this network here have in common the same network ID of 192.168.10.0, correct?
Correct.
And any device that's connected in this network better have that same network ID, right?
Right.
Okay. Now, let's say we did this. Let's say we assign PC0 up here to 192.168.10.100. What would the network ID be for that PC?
It'll be 192.168.10.0.
Correct. Now, is that allowed?
That one is allowed as long as the network ID is not different than the other one.
Is not different?
Yeah, I'm talking about network ID, not the IP address.
Okay. Now, this is a network here that consists of 2 devices. This is a network here that consists of 3 devices, the router, the switch, and the PC. Can these 2 networks have the same network ID?
Yes.
No. The answer
No?
is no. Yeah. Sorry about that. Get a little more room here. I want to I can't really do it. Sam, how many, if we say that every network has to have a unique network ID, how many networks do I have in this diagram here?
Network ID and
how many networks do I have in this diagram?
12.
Very good. Okay.
Right.
So we got 1, 2, 3, 4. Then 5, 6, 7, 8, 9, 10. Oh, wait a minute. Did I count that right? I think I might have counted that wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So yes, you are correct, Sam. Okay.
Right.
Now, every network has to have a unique network ID. Okay.
Have a unique network ID. Could you write this down?
Okay.
Okay.
Now, you see where my mouse is at, right?
Yeah. Every
Okay.
connection.
That is a network, correct?
Correct.
And this up here is a separate network, correct?
Correct.
All right. So what is the network ID here?
It would be 192.168.10.0.
And what's the network ID up here based on this IP address?
192.168.10.0.
Are they the same network ID?
They are the same network ID.
And is that allowed?
No, because they're different networks.
Correct. You are correct. Okay. So every network has to have a different network ID. All right? And right. Every network must have a unique network ID.
All right. Okay. Thank you.
All right.
I
Now,
got it.
good.
All right.
Now, I want you to change this IP address for PC0. I want you to change it to something different so that the network ID is different from the other network that we're working on.
It'll be changed to 172.15.10.0.
Okay, how about if we stick with the 192.168? Can you just change this just slightly and make it a different network ID?
We could make it like a different network ID. But
Tell me how we do that.
We can make the shadow notation of /23.
What would it be?
/23.
No, we don't want to do that. Don't play with the subnet mask. I want you to change this IP address so that it belongs to a different network ID. What is the standard subnet mask for Class C?
It would be 255.255.255.0.
So if I were to change octet number 1 somehow, would it be a different network ID?
If we were to change octet 1 to like 190,
Right.
it would be a different network ID.
How about if I were to change something in octet number 2? Would it be a different network?
If we change that, no.
Remember, the subnet mask is 255.255.255.0, which means the network portion, the network ID portion of this IP address is in the first 3 octets. Right?
Right.
So I could change any one of those 3 octets. Instead of 192, I could change it to 191. Instead of 168, I could change it to 166. And instead of 10, I could change it to 11. And it would give me a different network ID. And that's what I would do. Okay? Change it to 11. Now, I want you to tell me, what is the network ID for this network then?
It'll be 192.168.11.0.
Correct. And is that different? Is the network ID different than the network down here? Yes, it is. Okay. So, again, every network here, okay, has to have a different or unique network ID. Okay?
Must have unique or different ID.
Yep.
And I got that one.
All right, very good. Now, let's go back to our routing protocols, okay?
Right.
So, we said that for router 0 has 2 neighbors, okay? And when it sends out its update, it sends out, okay, its distance from all of the networks that it knows of. Okay?
Right.
So, and we said, how many networks do we have, and how many sub networks did we have in this diagram here?
The network.
How many did we say we had?
12.
Said we had 12. So when we do a RIP update, we send out the cost as well, the cost for each one of the networks. And we said that there are 12 networks. Now here's a question. What is the cost to get to the network 192.168.11.0 from router 0 to PC 0? What's the cost? Do you remember how we measure the cost with RIP?
We measure it, that means going through everything. Means going through the same map.
We measure it based on hops.
Hops.
And what is a hop?
It's counting from one router to another one.
So a hop is, the number of routers you've got to jump through. So in this particular case, we're going to 1, then 2, 3. Okay? and then basically 4. We're crossing routers. So we cross this 1, then this is 2, and then maybe it's 3. Maybe it's 3 hops, okay?
Right.
It's 3 hops.
1. This is 1. This is 1. This is 1, 2, 3, 4 hops.
Let's just say that it's 3 hops. Now let's say if I were to take this route, I was to go down below here, come down here, that would be 1 hop, then a second hop, then a third hop, a 4th hop, then a 5th hop. Okay?
So it'll be first hop, the second hop, the third hop, the 4th hop, the 5th hop?
Yeah, so there are 5 hops. That path that we just took would cost more because there are more hops. All right?
So there's more cost. So
cost is higher.
Okay, so it'll be 1, should be 1, should be 1, 2, should be 1, 2, 3, 4, 5, should be 1, 2, 3. Going from the top.
Yep.
And 5 going down the bottom.
Yes. Right now, I just turned on all the labels. I don't know if I should have done that because it looks pretty messy right now. Let's turn these off. I thought I turned those off. Okay, here we go. Okay. So again, distance vector sends out all of the networks that it knows about and how many hops it takes to get there. Okay?
Right.
So can you see how router 0 and using distance vector or RIP only sends updates to its neighbors, router 1 and router 2. But it sends out in each update that it sends to router 1 and router 2, it's a rather large update. Okay, there's a lot of information in it. Okay?
Right. So it sends updates to router 1 and router 2.
Right. Now, if we were using something like OSPF, when OSPF sends its update out, what's in that update?
Is the cost to its direct neighbor.
The cost to its neighbors. Okay? So it calculates the cost to router 1 and the cost to router 2. Okay?
Right.
And that's all it sends out. But who does it send that update out to? Who does it send it out to?
It sends it out to...
Look over here.
Everyone.
To everyone. Sends it out to everyone. Where RIP, okay, and distance vector only send to the neighbors, okay, OSPF, or the link state algorithm, sends to everybody, to all the routers in this AS. Okay?
All this route. For example, it sends it out to all the routers. How about switches?
Well, here's the question. Do switches do routing?
No.
Well, they do a kind of routing, don't they?
Yeah.
They do. There we go. I had this dragonfly in my office that's been flying around all day, and he finally flew outside, so I'm closing my door. Anyway, so distance vector sends out to its neighbors information about every network it knows about, while link state sends out to everyone, but it only sends information about those that it is directly connected to. Okay?
Those are directly connected to it. So router 1 and router 2 is directly connected.
Right.
And then after it goes out there, then routers 3 and router copy router 2 and copy 2.1 is their neighbor.
Yep.
Then right afterwards, then we could do from routers 2, from router, what is this? From copy router that, it will go up to router 2.4, which is to 2.8.1, which is the direct neighbor.
Mm-hmm.
And then for 2.8.1.1, it sends it right out to router 2.1.
Okay. Does that make more sense?
It's making some sense.
All right. It might help if we actually do a little exercise. With this. Let's see how we're going to do that. All right. It's going to take me a little time to set this up, all right?
Okay.
You okay with that?
I'm good.
All right. If you have to, you can go and do something and just come back to me in a couple minutes here, okay?
Okay.
Okay, Sam, I'm ready for you.
Jim.
All right, so I'm just going to move this over here. Now, let's do router 0 and figure out what kind of update router 0 is going to send for RIP, okay?
It's gonna send your
Hold on, before you get there. Let me just write this down. So router 0 is going to send to router 1 and router 2, right?
Right.
And it's going to send all of everyone that it knows that it's connected to, okay? As well as the cost, okay? So take a look at the addresses that I've assigned for on each one of the links. Do you see them?
Yeah.
Do you see the little numbers that are by the lines? 1, 2, 3, 4, 5. I think is the highest.
1, 2. I think I see 1, 2, 1, 2, 1, 2.
Yep. And that's because that identifies the port number for, okay, on that particular device.
Port number.
Yeah.
So this one will be port 1, port 2, and after that.
All right.
And then it'll be router. Then there'll be router 3.
Where?
Right here.
Router 3 has how many interfaces?
Router 3 has 1, 2, 3.
Router 3 has how many lines are going into router 3?
1, 4 lines are going into, wait, hold on. There were 5 lines going into router 3.
Correct. 5 lines going into router 3. And you can't have a line going into a router without an interface. So 5 lines, 5 interfaces. The little numbers indicate the interface, okay, on that device. So, for instance, on router 1, how many interfaces on router 1?
It is 2.
And what are the numbers for those interfaces?
There are 1 and 2.
Right, 1 and 2. How about on router 2? How many interfaces?
Three.
There are 3, and the interfaces are numbered 1, 2, and 3, correct?
Correct.
Okay, very good. How about on router 5? How many interfaces?
Three.
There are three. And the interfaces are numbered 1, 2, and 3, right?
Right.
So we got that. So 1 second, I'm putting something else in. All right, so I got 10 and 11, okay. 2, 3, 4, 5. I'm doing this on my other screen, and then I'll move it over and show it to you. 8, 9, and 10. So how many networks do we have in this network again?
We have 12 networks.
We have 12. Somehow I'm missing one. Got 11. Notice they're numbered, right?
Right.
So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, right?
Right.
So we got 11 networks, all right?
Right. 11.
All right, so there are those networks right there, okay?
Right. 11 networks.
Right. Now, so router 0 is going to basically say that its cost, okay, is going to send out the cost for all the networks that it knows of, okay? Right?
Right.
So taking a look at this, again, in a distance vector system, how do we, and specifically with RIP, how do we figure out the cost?
It's to its direct neighbor, and it's to your neighbor.
What's the term that we use?
RIP is the best cost to your direct neighbor. Your best cost to your direct neighbors.
Yeah, but you're reading that. You're reading that, Sam. Right?
The best cost to each destination.
Okay. But what did I say before? How do we measure the cost when it comes to distance vector and specifically RIP? What unit of measure do we use?
We use
hops.
Hops.
Okay. So and I'm going to put this up here. I'm going to say cost equals number hops. Okay?
Okay. Number of hops.
We're talking about router 0, right? And router 0 is going to has to have a cost for network 1, 192.168.1.0. I'm just going to call it network 1 to make it easy, okay?
Okay, network 1.
And how many hops does it have to do to get to network 1?
Just 1 hop.
1, it actually has 0. It's directly connected.
0.
Okay? All right, great. Now, to get to network 2, what does that cost?
From router 0 to router 2?
Yes, from router 0 to router 2, what does that cost?
0.
0. It's 0 hops. How about to network 3? What is the cost
1.
there? Very good, 1. And to network 4? Guess what, Sam? I just noticed where our 12th network was. Right there. You see it? Between
Yep.
router 2 and 3, okay?
Wait. Router 2 to router 4. It'll be 1 hop.
All right, so to network 4, it's going to be 1 hop as well.
1 hop as well.
Okay. Now to network, how about to network 5?
This still is 1 hop.
Network 5?
Network 5. Hold on. One. 2.
Okay, so it's 2.
2.
Okay, good. How about network 6? What is the cost? Now, here's a question for you, okay? How many paths are there to network 6? And the answer is the same for network 5.
Yes, it'll be 2.
There are 2 paths. Are their costs any different?
No.
They're the same costs. They're going to be 2. Okay? So the cost for network 6 from 0 is 2. But to 7.
7. One. 2.
Yes, it's just
2.
All right. Okay, I'm going to throw you a curve. How about the network 8? What is the cost?
B. 1. 1. Just 1.
To network 8?
Just
From
2.
From 0 to 8. Okay.
That's 2.
And what path would you take?
I would go from router 2 to router 4.
Very good. Now, could I also go from router 1 to router 3 to router 4? I could, couldn't I? But
Yeah.
why don't we do that?
Because it's not the best cost. It's not the least cost.
Exactly. So we're tracking the best cost. So in this case, it's going to be 3. How about for 9?
3. For 9.
Here's 9 right here. What's the cost?
1, 2, 1, 2, 3.
Okay. Now, what's the path though?
It's routers 2, routers 4, and routers 5.
Okay. Is there another path that I could take?
You could take it from routers 1, router 3, and routers 5.
Okay, so that path has the same cost, correct?
Correct.
All right. Okay, now let's go to network 10. What's the cost?
Three. 1, 2, 3. 4.
All right, very good. Now, how about network 11? What's the cost?
1, 2, 3. 4.
Really?
3.
3. Yes. And finally, for network 12, what is the cost? Do you remember where network 12 is at?
Now, network 12 is at between router 2 and router 3.
Very good. Okay, so what's the cost?
1.
1. Okay. Okay. Now, okay, right?
Right.
Okay, now, let's take this, and I'm going to copy it. And we're going to come down here, and I'm going to put that there. And now, we're going to change this, and we're going to say link state, OSPF, right?
Right.
Now, if we're using a link state or OSPF routing protocol, who are we sending this update to?
Everyone.
All right. So over here, I'm going to take this out. And we're going to send it to
Router 3. Because they are your direct neighbors.
router 3, router 4, router 5, router 6, router 7, router 8, router 9, router. How many routers do I have? I only have 7 routers. Okay. Sorry about that. Correct? I got 1, 2, 3, 4, 5, 6, 7, 8. Oh, yeah, because we count router 0 in there. But router 0 is not going to send an update to itself, is it?
No.
Okay. And what is, in this update, in a link state update, what are we sending out?
Because they are direct neighbors. So we're sending out.
And what are the networks, the direct neighbor networks then?
It's provider 0, it's 1 and 2.
Networks 1 and 2. All right. So look at that, okay? You can see it very clearly now, Sam. We can see that router in a distance vector, okay, we send out only to our neighbors, a limited number of neighbors, okay? But it's the update, the information, the amount of information we're sending is a lot. Look at all that information we're sending. All those networks we have to send out. So only a couple of routers get the update, but the update has a lot of information in it, okay? In a link state, we send out to a lot of neighbors, all of them, everyone, but the update is very small.
Very small.
Okay?
I don't. How are we doing it very small? Are we doing like 1 and 2 and then we move on?
Yeah.
So links to,
let me just write this down for you, okay?
okay.
So I'm just going to say distance vector. We're going to link state. Okay. Does that help? Do you see that better? the difference between distance vector and link state?
I see if it sends big updates, but it sends to everyone but small updates.
Right.
It helps some, a little bit. It helps some.
Okay. All right. Well, I can't think of another way of explaining it any better than that. I think that's probably the most detailed I've ever been in terms of explaining how this works.
Yeah.
Now, when we look at path vector, which is another type of routing algorithm, specifically that used in BGP, okay? BGP uses path vector. What it does is it sends, again, to the neighbors, only to its neighbors, okay? But it sends the path, okay, to each destination that it has. So it's kind of like a combination of the two. Or no, it's more like, I'm sorry, it's more like the distance vector. Okay? Distance vector sends out to its neighbors. Okay? And it sends out the path for each destination. Okay?
So it sends it out to, can we do an example of path vector?
All right. Path vector would look look very similar to distance vector. Only instead of, just giving you hops, it's basically going to tell you the path to take.
Path you take.
Tomorrow night, what time do you want me to come over?
Can I send you a text message?
Or not tomorrow night, but Monday night. Okay. What time do you want me to come over? You want to send me a text message for that?
I want to send you a text message for that. Let me see what time I get out of work tomorrow. And
You're not working tomorrow. You mean Monday.
I'm working Monday.
Right.
And I'll be working on Tuesday.
Right.
Let me check my schedule and let me get back to you about Monday.
Okay, very good. Very good. All right.
All right.
Okay, so getting back to this. All right. I want you to look this over, and I'm going to take all of this. Let me just do a screenshot, and I'm going to put it into a Word document for you. And I'll grab a screenshot, and we'll do new. And we're going to here's our screenshot, and then we're going to paste this in here. In fact, let's do this. Let's do, okay. in landscape mode, it'll look better. Okay? And I'm going to take this and I'm going to save it into our Google Drive.
Okay.
And we're going to save as. And we're going to browse. And we're going to go up to our Google Drive. And our sample folder. And we're going to call this right. Algorithm comparison. Okay, Sam, so you've got that in the folder.
Give me 1 second. Could you routing algorithm? Did you call it? What did you call it?
Routing algorithm comparison. So you can see the name at the top of the window here.
Where did you put that? Where?
I put it in the. I put that into our Google Drive.
Routing comparison?
Yes, routing algorithm comparison.
Routing algorithm.
Here it is right there. Okay, you can see it right there.
Routing
algorithm comparison.
Algorithm comparison. Stupid. 6 o'clock. Yeah. I don't see that one on the top. I only see on my part routing comparison,
Yeah.
but I don't see routing algorithm comparison on my end.
Let me try this then. Let me close this document. Maybe that'll force it to send. And let me ask Google what it's doing. Google says it may be still syncing.
Yeah.
Yeah, it's still sending. Okay, I'm sorry. That's what's going on, Sam. It's still sending it.
Okay.
So it'll be there in a little bit. All right. So don't worry about it.
All right.
All right. Very good. Now, what would you like to go into next? We haven't talked about switching in a while.
Can we talk about switching?
Okay. Very good. Okay. Now, network switches have work at what layer?
Layer 2 devices.
Okay. And you'll notice that we have one hub in this network, correct? Down
Right.
in the lower right hand. And the hubs operate in what layer?
The physical layer.
The physical layer. Okay. Switches do what they do by using what type of addressing?
You would be using a data link and physical layer, but the addressing is for source IP address and destination IP address.
Careful. Do switches use IP addresses?
No.
What do they use instead of IP addresses?
They use the source MAC address and the destination MAC address.
Right. They use MAC addresses, right?
Right.
Okay. And MAC addresses are assigned to what?
Source MAC addresses are assigned hexadecimal numbers.
Are hexadecimal numbers correct? And how many hexadecimal digits?
It can assign up from 0 to 15, 0 to 9, and then A, B, C, D, E, and F, up to F.
Yeah, not quite what I was asking. Let me ask this question. How many bits, a MAC address is how many bits long?
It is 48 bits.
48 bits. Okay. Now, I want you to convert that into how many hexadecimal digits does it take to represent 48 bits? How many bits does it take to represent a single hexadecimal digit?
How many
decimal?
decimal?
Decimal. How many bits does it take to represent a single hexadecimal digit? What's the biggest digit in hexadecimal?
It's F.
And what is the binary for F?
111 to be 1111. One.
Four ones, right?
41.
So it takes 4 binary digits to make one hexadecimal digit, correct?
Correct.
So if you have 48 bits, how many hexadecimal digits does that give you?
48 bits. Hold on. It gives you. Hold on. F3.
How many?
F3.
What's F3?
F is there'll be 3 F's and a 3.
No, listen to my question again. You have 48 binary digits, bits, 48 bits, right?
Right.
And we said that it takes 4 bits to represent a single hexadecimal digit. So if that's the case and you've got 48 bits, how many hexadecimal digits do you need to represent 48 bits?
I'm not understanding the question. Could you rephrase it?
Okay. Let's do this. Okay. I'm going to give you a problem. Let me get my notepad up here. And let's see. Okay, so there's a binary value.
Right.
48 bits long. Now I want you to convert this into hexadecimal. How would you do that, Sam?
Hold on. Maybe first.
This is what you need to do, Sam. Okay?
Yeah.
Starting from the right, moving left, I want you to break this string of bits into chunks of 4. Okay?
Okay.
So I'm going to break it there.
You're gonna make it there.
Break it there. 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 Okay?
Okay. Give me 1 second.
Now, I want you to convert each group into its hexadecimal value. So, this first group here is an A.
Yeah.
So, I want you to write down the rest of them and then tell me what your answer is, okay?
Okay.
Sam, it's taking you quite a long time. Let me show you how I do this, okay?
Okay.
Probably using your calculator, aren't you?
I'm counting the numbers.
Okay, look, watch this. It's real easy, okay? So let's just count in hex. And we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A. Do that in capitals. A, B, C, D, E, F. Okay? Now, X0 is equivalent to what in binary?
It'll be 0.
Okay?
It'll be 0, 1.
Really?
1. And that'll be 1, 0. And 3 will be 1, 1. And 4 will be 1, 0, 0. And 5 will be 1, 0, 1. And 6 will be 1, 1, 0. And 7 will be 1, 1, 1. And 8 will be 1, 0, 0, 0. And 9 will be 1, 0, 0, 1. And 10 will be 1, 0, 1, 0. And B will be 1, 0, 1, 1. And C will be 1, 1, 1, 0. And that'll be 1, 1, 0, 1. And that'll be 1, 1, 1, 0. And all four 1s.
Okay. Now, if you write this down, okay, like this, now go through and just substitute. What is a 1011? Well, you can come down here.
11.
Is a B.
B.
right?
Right.
Okay, so finish up and tell me what the rest of these are.
5, 5, B, 4, 9, 4, 5, 2, 10, A, 8.
Did you say 10 or what?
A. I said A.
A.
I made
Very
a
good.
mistake. I just said I and B.
What do you think? Don't you think that was faster than what
Yes,
you were doing? Okay.
that was.
Now, one of the things that I always do, okay, is a lot of times when I'm taking tests like this, I also put in the decimal as well so that it's easy. So I put in 0 and 1 and 2, 3, 4, 5, 6, 7, 8. Oh, sorry. 9, 10. Oh, wait a second. I screwed up. 11, 12, 13, 14, 15. Okay?
This is 15.
Right. Now, if I give you a problem like this, okay, like I want you to convert 3 DVA, which is what kind of number?
Hex.
It's hex. And I want you to convert that to something in decimal, okay? A parenthesis 10 means base 10.
Base 10.
Can you do that for me quick?
There'll be 3. 3.
I'll tell you what, I'll make it even easier for you, okay?
Okay.
Just give me BA. I want you to convert that into decimal.
Will be 10, 11. 10, 11 will be equal to 21. Base 10.
Really? 21? How did you get that?
I based it on 11 and then 10.
Okay, let me ask this question then. Okay. I want you to convert BA into binary.
BA will be
What's the binary for B?
it will be 1011.
And what is the A?
The A is 1010.
Okay, and that's base 2, correct?
Base 2.
Now, convert the binary into decimal.
So that would be 1010 will be 10 and 11 will be 10 and 11 will be 21.
No.
1010. I thought, how come it's not 21 if I'm doing 10 and 11?
No, I need you to focus on the binary. Okay.
Right.
I need you to convert that binary number into a decimal number.
One zero one zero one zero one zero. One 32. One 86.
Hold on. Not quite what I got. Oh, wait a minute. Yes. You are correct. Yep.
Yep.
So it's not 21, right?
No.
Whenever you're doing going from hex to decimal, I always suggest going to binary first, then to decimal. So convert the hex into binary, then convert it into to decimal. It's a lot less confusing that way.
Yeah. Convert
And
hex to binary. Yes. Okay.
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 So let's go back to our original question. How many hexadecimal digits does it take to represent 48 bits? 48 binary digits.
48. A, B. Let's convert these to.
We'll count them. Look.
There'll be that will be 11, 10, 2, 5, 4, 9. There'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 binary digits.
No, 12 hex digits. 12 hex digits.
12 hex digits.
So 48 bits equals 12 hex.
I can't see it. Can you move it?
Really, you can't see it?
Yeah, I think you moved it so close.
Okay, 1 second. There. Can you see that?
I don't see that.
Do you see my mouse moving back and forth?
Good. Your mouse, I don't. Wait, now I see it. Now I see it.
Okay. So 48 bits equals 12 hex digits.
48 bits equals 12 hex digits.
So we didn't have to go through this entire exercise because my original question was, if I've got 48 bits, how many hex digits does that represent? And I simply calculated it by saying, okay, 48 bits, okay, divided by 4 bits per hex digit equals 12. I just calculated that in my head. I didn't have to go through this exercise.
It would be like 12 hex digits. It would be.
Yep, 12 hex digits.
There's 12 hex digits.
Right.
And then, for example, if we're 64, it'd be 16 hex digits.
Yeah. Yep. But what's important here, okay, what's important is that a MAC address is 48 bits, 48 binary digits, or 12 hex digits.
Right. The MAC address is 48
bits long, which is equivalent to 12 hexadecimal digits.
Which is equivalent to 12 hex digits.
Right.
Wait.
Okay. I need to get going because we're past 6:30. Okay.
Okay.
Would you text me tomorrow and tell me what time we're going to get together on Monday?
Yes, I'll text you tomorrow.
All right. Very good.
Let me text you. Let me check my schedule.
Yep. Okay. Good.
All right.
Super. Then I'll talk with you soon. You have a good night. All right.
Thank you. You too.
All right, Sam. Thank you. Bye.
Right. Bye-bye.